Hi everybody, in this video I am going to be going through the review sheet for test number 1. So I'm going to try to go in as in-depth as possible to every question, so this video is going to end up being like super long. So feel free to skip around to the parts that you need throughout the video, the questions that you had trouble with. I would definitely consult the answer key first, and the questions that you got right, you don't really need to watch in the video unless you want to. The questions you got wrong, I would definitely recommend watching. Okay, so let's take a look at number 1 and let's check out the answer choices. So we're told in the question that in the two triangles, we know that AC is parallel to BD. So I already see that we have alternate interior angles. Let me just highlight my parallel lines and my transversals so that you guys can see that letter Z. In the corners of the letter Z, we do have alternate interior angles. And I do also see that we have vertical angles. So that means that the two triangles are similar to each other. We have similar triangles, corresponding sides are proportional, so that allows us to set up proportions involving the corresponding sides from the two triangles. So what we're going to do is we're going to take a look at each of the 4 answer choices, and we're going to determine which answer choice has a correctly set up proportion. Remember that there's many different ways to write the proportion, so we just need to make sure that the corresponding parts from the different triangles are kept together in order to make a valid proportion. So let's take a look at number 1. So number 1 has CE. So CE is the second and third letters from the big triangle. So I'm going to write that over here, big triangle. And DE is the second and third letters from triangle BED, so that does correspond to CE, and that's from the small triangle. So just to be consistent with the way that they set up the proportion here, in order for this proportion to be correct, on the other side, we should be starting off on the top with a side from big triangle, and on the bottom should be the corresponding side from the small triangle. So let me take a look. We have EB, but wait, EB is from the small triangle, so that's not consistent, because in order to be consistent, if it was big over small, this should be big over small as well. So I'm going to eliminate choice number 1. That's not true. That's not a correctly set up proportion, so goodbye. We need to pick which equation is true. Let's take a look at number 2. So we have AE, and let me just erase so that we don't get confused. Okay. So we have AE on the top, and AE is from big triangle. I'm going to just write B for big. And BE, so AE was the first 2 letters from big triangle. BE is corresponding because it's also the first 2 letters from small triangle. So in order to be correctly set up, on the other side of this proportion, we should have the side from big triangle over the corresponding side from small triangle as well. So AC is the first and third letters from big triangle. So it should correspond to BD. And look, BD is also the first and third letters from small triangle. So it does. This is a correctly set of proportions. So we have already found our answer. You take a look at the remaining 2 answer choices, just in case you were a little bit confused about why the answer is not them. Let me just remove this so we could see it better. We can take a quick look. So EC is from the big triangle. AE is also from the big triangle. So in order for this proportion to be correctly set up, on the other side here, there should be the corresponding side to EC from the small triangle and the corresponding side to AE from the small triangle. BE is from the small triangle, but it doesn't correspond to EC. EC is the second and third letters in the triangle's name here. So it should correspond to the second and third letters of the triangle's name here, which is ED. So in order for this to be correct, this would have to be ED, and therefore that should be BE. So that choice is incorrect. It's not correctly set up. And finally, for choice number 4, we have side from small triangle over, so that was ED. So that's second and third letters. So we have it over corresponding side from big triangle. So I'm going to write that here, small over big. So on the other side, we should have a side from small triangle and the corresponding side from big triangle in order to be consistent. But look, AC, that's from big triangle. So already I see they're not consistent. This is not a correctly set of proportions. So choice number 1, it is. Taking a look at question number 2, we're told that the two triangles are similar, and we need to pick which statement is going to make the triangle similar by SAS. So in order to do this, the best way to approach these kinds of multiple choice questions is by plugging in the answer choices and see which one does what it's supposed to do. So the first situation says, imagine that DE is 9 and that DF is 12 and that angle A is congruent to angle D. I see the congruent angle in between the two sides that we have information about, but in order for SAS to hold, the corresponding sides do need to be proportional. So AB, first and second letter, corresponds to DE. So I'm going to find the scale factor of these corresponding sides. I'm just going to take 9 over 6. On my calculator, that is 1.5. Okay. AC is the other side we have information about. That's first and third letters. So it corresponds to DF. So I'm just going to divide those two corresponding sides as well in order to get the scale factor. And wow, we got really lucky here. The scale factors are the same. So the corresponding sides surrounding the congruent angle are in fact proportional since they have the same scale factor. So we already found the correct answer choice. If you plug in choice 2, choice 3, and choice 4, you will see that either the corresponding sides from the two triangles won't have the same scale factor when you divide side from big triangle over corresponding side from small triangle, or you will see for some of the other answer choices that the angle isn't directly in between the two congruent sides. For question number 3, it's talking about two triangles, but I don't see any diagrams. So I'm going to get started by drawing the two similar triangles. We have triangle ABC and ZXY. So now I have both of my triangles labeled. I'm told that angle A is 50 and that angle C is 30. And we need to find the measurement of angle X. So that's the angle we're looking for. Well, remember that similar triangles have congruent corresponding angles. So angle A and angle Z will have the same measurement of 50, and angle angle C and angle Y will have the same angle measurement of 30. So in order to find X, remember that all the angles of a triangle add to 180. 50 plus 30, that's 80. So the missing angle should be 100. And that's our answer here. In question number 4, we're told that the two triangles, ABC and DEF, are similar to each other. We're told that AB is 7x, BC is 4, DE is 7, and EF is x. And what we need to do is find the length of AB. So if we can find x, then we can plug in to 7x and find what AB is. So I'm just going to set up a proportion because we do know that the corresponding sides of similar triangles are in proportion. So let's start with AB. And AB is the first two letters. So it's going to correspond to DE, first two letters. So I'm going to 7x over 7. Then, being consistent, I took 7x first. So I'll take 4 from the same triangle. And that's BC, which is second and third letters. So it's going to correspond to EF, which is x. Once I have my proportion, all I need to do is cross multiply. 7x times x is 7x squared. And that's equal to 4 times 7, which is 28. Dividing both sides by 7, x squared is equal to 4. And then taking the square root of both sides, we get x is equal to plus or minus 2. We reject the negative because we are talking about real world shapes. It wouldn't really make sense if a triangle had a negative side. So we have that our x value is 2. That doesn't really look like 2. There we go. So plugging in for AB, which is what we need to find, 7 times 2 is 14. So 14 is the length of AB that we are looking for. In number 5, we are told that we have right triangle ABC, and we're told that CD is the altitude to the hypotenuse of the big right triangle. So we should automatically be thinking, once we see this diagram, once we hear the words altitude drawn to the hypotenuse of big right triangle, we should be thinking right triangle altitude theorem. So we should be in our minds trying to figure out what we're solving for, and if that's going to mean that we use the leg rule or the altitude rule. So I see that we know that CB6, we know that AD is 5, and we need to find the length of BD. So I'm going to label that as X. Well, I'm trying to determine if I'm going to be using the altitude rule or the leg rule, and I see the altitude is CD, but I'm not finding CD. That's not what I'm looking for. That's not X. X is DB. And I don't have any information about the altitude that I could plug in to solve for something else. Since I have absolutely no information about the altitude and I'm not looking to find it, it's not what the question's asking for, that leads me to believe that we're going to be using the leg rule, especially since we do have a measurement for one of the legs of the big right triangle. Just to refresh your memory, if I outline the big right triangle, you guys can see that across from the 90-degree angle is AB. That's the hypotenuse. So that means AC is one of its legs, and BC or CB is the other leg. So we do have a leg measurement. So we are going to be using the leg rule. I'm going to set up my proportion, and we do know that the leg is the mean proportional between the whole hypotenuse. So one part is 5, one part is X. So together that should be 5 plus X. That's the whole hypotenuse. And the leg's projection on the hypotenuse. In other words, the part of the hypotenuse directly below the leg that we're focusing on. Notice how there's two parts of the hypotenuse. There's AD and there's DB. The part that we are going to be using in our proportion here is going to be the part directly under the leg that we're focusing on, the leg that we have information about. So that's going to be DB, which is X. From here, all we need to do is cross multiply. So we have 5x plus x squared is equal to 36. In order to solve, I don't want this to get confusing, so let me move my work over. Give me one. There we go, a little bit more space. So I'm just going to make this quadratic equal to 0 by subtracting 36 from both sides. So I have x squared plus 5x minus 36 equals to 0. So I'm just going to look for two factors of negative 36 that add to give me positive 5. So let me think for a second. And the two factors that come to my mind are 9 and 4. I need the sum to be positive, so I'm going to be using a plus 9 and a minus 4. 9 minus 4, if I add those together, does give me 5. And if I multiply 9 and negative 4, I do get negative 36. So that tells me that my solutions are x equals to negative 9 and x equals to 4. Since we are working with a real world situation, triangles are real world objects. It doesn't really make sense to have a negative value. So we reject the negative and we find that x is 4. And remember, we're looking for BD, and BD is represented as x. So once we find our x value, we also have our length of BD. In number 6, it tells us that we once again have a right triangle ABC with an altitude CD drawn to the hypotenuse. So once again, I'm going to think right triangle altitude theorem. Am I going to be using the leg rule or am I going to be using the altitude rule? So they tell us that AD is 3, DB is 12, and that we are looking for the length of altitude CD. So I'm going to label the altitude with an X since we're looking to find it. And that tells me that we're going to be using the altitude rule since we're solving for the altitude here. So I'm going to set up my proportion. Remember that the altitude is the mean proportional between each of the two parts of the hypotenuse of the big right triangle. So it's the mean proportional between 3 and 12. So I'm going to cross multiply. 3 times 12 is 36. X times x is x squared. Taking the square root of both sides, we get plus or minus 6. We reject the negative, so we have x is equal to 6. And that represents CD, the altitude, which is what we're looking for. Okay. In the accompanying diagram, both of the triangles are similar. We have a couple of measurements here, and we are finding the length of ML. So here's ML. I'm just going to label it with an X. Since the triangles are similar, we do know that the corresponding sides are in proportion. So I am going to set up a proportion to solve for the missing sides. So let me set up a proportion. So let's start with RQ. And RQ is the first and second letters. So it's going to correspond to the first and second letters from this triangle, which is LM, which I don't know. So I'm going to label it as X. I want to use LN. That's the first and third letters from that triangle. So I'm going to put it here. So it should correspond to the first and third letters from the first triangle, which is QS. And QS is 21. And just so everyone's clear on how I set this up, I did a side from big triangle over a corresponding side from small triangle, side from big triangle over the corresponding side from small triangle. I'm going to cross multiply. We have 210 is equal to 21x. Dividing both sides by 21, we have x is equal to 10. And that represents the length of ML. So I'm going to write here the length of ML is equal to 10. That's what we were looking for. In the diagram below of right triangle ABC, altitude BD, so first of all, right triangle ABC. Where's that right angle? I'm going to draw it. Altitude BD is drawn to hypotenuse AC. If BD is an altitude, I'm going to put in some right angles. There we go. That looks more like what we're used to seeing. So now we should be thinking right triangle altitude theorem. Are we using the leg rule or the altitude rule? So we're told that BD is 4. Oh, look, we have information about the altitude. So we might be using the altitude rule here. AD is x minus 6 and CD is x. What is the length of CD? Since we have information about the altitude, let's try to use the altitude rule and see if we have enough information to do that. So we do know that the altitude is the mean proportional between each of the two parts of the hypotenuse. So it's the mean proportional between AD, which is x minus 6, and between DC, which is x. From here, all we have to do is cross multiply and solve for x. So we have x squared minus 6x is equal to 16. Since we do have a quadratic, the highest exponent is 2. Let's subtract 16 to get this equal to 0. So I have x squared minus 6x minus 16 is equal to 0. Let's look for our factors. So I'm looking for two factors of negative 16. So that the numbers need to multiply to give us negative 16. And they need to add to give us negative 6. So I'm thinking 8 and 2. Since the sum needs to be negative, the larger number 8 should be the negative one. And that means 2 is going to be the positive one. Negative 8 plus 2 does give us that negative 6 that we're looking for. And negative 8 times negative 2 does give us that negative 16 that we need. So our two solutions are x is equal to 8 and x is equal to negative 2. Since this is a real world example, a triangle is a real life figure, it doesn't make sense to have a negative side length, so we're going to reject the negative. And we have our solution is 8. And just to double check, we're looking for CD. CD is represented as x, so we did find the length of CD when we found x. CD is 8. We don't need to plug in anywhere else or do anything else. Number 9 says determine if the following pairs of triangles are congruent, similar, both, or neither. So let's do it. So for the first pair of triangles, I do see the congruent 70-degree angle for both. Let me just mark that in my diagram. So I'm thinking maybe SAS. Let me just check if the corresponding sides from the surrounding sides of the angle are proportional. So I'm going to find the scale factor. Let me do 12 divided by 3. That's 4. And let me do 16 divided by 4. And guess what? That's also 4. So these two triangles are similar, and they are similar by SAS. What's in the middle here? So once again, I see the congruent angle in between the sides. So maybe it's going to be SAS. I just need to double check that the corresponding sides are in fact proportional. So I'm going to do 16 divided by 6, big side divided by corresponding small side. And when I do this on my calculator, I get like 2.666667. So I'm just going to write like 2.6. We really shouldn't round, but I just want to see if we get the same scale factor. It's like 2.66666667 on my calculator. Okay. Then I'm going to do the other corresponding sides, 14 divided by 4. And what do I get here? 14 divided by 4. And I get 3.5. Clearly, these are not the same. So I'm going to write these triangles are not similar. It's not SAS because the corresponding sides are not proportional by the same scale factor. We don't have any other information here to conclude like it's similar by angle because I don't know anything about the other pairs of angles. Okay. In the third pair of triangles, I see 3 pairs of congruent corresponding sides. So these are definitely similar. The reason for that is since we have 2 equal sides in each of the triangles, the angles opposite are also equal. And since this side is equal to this side and this side is equal to this side, these angles are all the same too. So we could make the case for AA. Another reason to know that the triangles are similar is because the triangles are congruent by SSS. And I'm going to write that here, they're congruent. So I guess they're congruent and similar. Now, they're congruent by SSS because all 3 pairs of corresponding sides are the same as each other. They're congruent. That makes triangles congruent by SSS. They're also so proportional if they're congruent. If all the sides are the same, well, then they're proportional by a scale factor of 1. So these triangles are both congruent and similar. Anytime you have 2 congruent triangles, they're also similar. But since they're exactly the same shape and size and all the side lengths are the same, that scale factor that the sides would be proportional by is 1 if we have similar triangles. In the diagram of triangle ABC below, DE is parallel to AB. We know that CD is 4. We know that CA is 10. CE is x plus 2. And EB is 4x minus 7. And we need to find the length of CE. So I'm just going to like outline that in red so we can see what we're trying to find. So I just want to like draw your attention to the fact that the small triangle that I'm highlighting in blue and the big triangle are similar by AA. We do have parallel lines cut by a transversal. Ooh, oh no. Where did it go? There we go. Sorry about that. So we do have parallel lines cut by a transversal. Here are our parallel lines. We have one transversal going this way, and we have one transversal going this way. So we do have congruent corresponding angles, making the triangle similar by AA. And we know when triangles are similar that the corresponding sides are proportional. So we can definitely set up a proportion here to find the missing side length. And we are looking for CE here. Notice how CE is aside from the small triangle. So just to be like consistent with how we're setting this up, I'm just going to put a side from small triangle over a corresponding side from big triangle. So I'll take 4 first. That's CD, that's a side from small triangle. And I'll put it over CA, which is the corresponding side to CD from big triangle. So that's 10. The only other side from small triangle that I have information about is CE, which is represented as x plus 2. And the corresponding side to CE from the big triangle is CB. I know 2 parts of CB. I know CE is x plus 2, and EB is 4x minus 7. And you need to add them together to get the whole side of big triangle CB. So x plus 4x is 5x. 2 plus negative 7 is negative 5. So I'm going to put that here, 5x minus 5. From here, all we need to do is cross multiply. So I have 20x minus 20 is equal to 10x plus 20. From here, we just need to solve the equation. Subtract 10x from both sides, and we get 10x. Add 20 on both sides is equal to 40. Divide both sides by 10, and I get x is equal to 4. So now we need to find CE. So let's make sure to plug back in. CE is x plus 2. 4 plus 2 is 6. So 6 is our length of CE. Triangle ABC is similar to triangle DEF. When you don't see a diagram, the very first thing that you should do is draw your own. So we have triangle ABC, and we have triangle DEF. The lengths of the sides of AB are 5, 8, and 11. I don't know which side's the smallest and which is the largest and which is in between, so I'm just labeling it however for now. It's asking us what the length of the shortest side of triangle DEF is if the perimeter is 60. So when I add all the sides up of DEF, we should get 60. If we can find what all the side lengths are, we can see which one's the smallest, because that's what we're looking for. I can find the perimeter of triangle ABC also by adding up all the sides. 11 plus 5, that's 16, plus 8, that's 24. Now, I know that when triangles are similar, their corresponding sides are proportional. And since their sides are proportional by some scale factor, their perimeters are also proportional by the same scale factor, because if the sides are proportional by a scale factor, that's going to impact, when you add them up, the sum that you get. And it will be by the same scale factor. So I'm going to just see what the scale factor would be by dividing the perimeters together. So I'm going to take 60, and I'm just going to divide it by 24. And I'm going to go over to my calculator, and I'm going to see what I get. 60 divided by 24 is 2.5. So to get from a side of the smaller triangle to a side of the bigger triangle, we're going to be multiplying by 2.5. I can tell triangle ABC is the smaller triangle here because the perimeter is much smaller than the perimeter of triangle DEF. So that leads me to believe that triangle DEF is the bigger triangle, and bigger sides, if you add them together, would give you a bigger perimeter. So if I multiply 5 by 2.5, I get 12.5, so that's the side over here. If I multiply 8 by 2.5, I get 20, so that's the side here. And if I multiply 11 by 2.5, I get 27.5, and that's this side over here. Let me just double check that this checks out. I'm going to just add the 3 sides I found together, 12.5 plus 20 plus 27.5, and I do get 60. So I see that the smallest side of triangle DEF is 12.5, so that would be the answer here. In question number 12, we are told that DE is parallel to AB. So from that information, you should be able to see that the small triangle and the big triangle in this diagram are similar by AA. Just like in other examples, we have the congruent corresponding angles, so we have AA. I'm going to erase that so it doesn't get in our way and cause confusion, but just keep in mind that we do have those congruent corresponding angles there. Okay, so now that we know that the triangles are similar by AA, we do know that the corresponding sides are proportional. In order to be consistent, I'm going to set up my proportion with a side from small triangle over the corresponding side to it from the bigger triangle. So I will use CD first, that's the side from the small triangle, that's X. And the corresponding side to it from the big triangle would be X plus 3 to get the whole thing. And that's 2X plus 3. So I'll put that over here over 2X plus 3. That's equal to, I'm going to take another side from the small triangle. DE is the only other side from the small triangle that we have information about. So that's 4 over the corresponding side to DE from the big triangle is AB, which is 10. From here, I'm just going to cross multiply and solve for X. So we have 10X is equal to 8X plus 12. Subtracting 8X on both sides, I have 2X is equal to 12. Dividing by 2 on both sides, X is equal to 6. Okay, for the next one, we are told that AD is parallel to EG, so let me just draw that in. We know that this angle here is 70, this one's 39, and we are looking for this angle over here. So I'm going to label it with a question. So it does also say to justify each step of the property. So we're going to think about how we are getting the answers that we're getting as we go along. So the first thing that jumps out to me is that we have the 70-degree angle and the 39-degree angle. So I'm going to start with those. If I add the 39-degree angle, the 70-degree angle, and this missing angle together, I should get 180 because they are supplementary to each other. They together, all three of these angles make a linear pair, make a straight angle. So what I'm going to do is I'm going to add 70 plus 39, and I get 109. And I'm going to subtract that from 180. So 180 minus 109 gives me 71 degrees for this angle over here. Next, I'm going to think about the other piece of given information that they gave us, that we have parallel lines here. So I'm just going to highlight the parallel lines, AD and EG, and I'll highlight one of the transversals that's intersecting those two parallel lines. Just to make it a little bit easier to see, I'm going to also outline in pink so you guys can see that backwards letter Z. Remember, anytime we see that letter Z, we're going to think alternate interior angles in the corners of the letter Z are those alternate interior angles, and they are congruent when we have parallel lines cut by a transversal. And there we have it, 71 degrees is our final answer. So I'm going to write that over here, 71 degrees is the measurement of angle FBC. Remember, alternate interior angles mean inside the parallel lines, so in between the parallel lines, not outside of them, on different sides of the transversal. So we have this angles to the right of transversal BF, and this angles to the left of transversal BF. So that's why they're alternate interior angles, but you can definitely just look out for that letter Z. The next question is a coordinate proof. So I actually did it two different ways. There's actually a third way also, and I'll mention it briefly. So I think the easiest way to do this one with the least amount of calculations is using angle. So I plotted the two triangles, and you should always do this because otherwise it's really easy like not to be using the corresponding sides of the two triangles. So definitely make sure that you plot and graph the triangles. It always helps to get a clearer picture of what's going on. If you're given a graph to use, why not use it? So what I did first in my first method for AA is I found the slope of line segments FG and HJ. And when I found the slopes using slope formula, I found that the slopes were 0. And remember, if line segments have the same slope, that means they are parallel to each other. And since we have parallel lines cut by transversals, we have congruent corresponding angles, making the triangle similar by AA. So that's the first way that I did this, and I have my reason written up over here as well. Remember, whenever you're writing a coordinate geometry proof, you should put a concluding statement summarizing what your calculations are showing and basically like explaining what you just proved with your formulas and your calculations. Instead of using both pairs of corresponding angles for AA, you could have also used angle E congruent to itself by the reflexive property. Or another approach is after you show that these two lines are parallel to each other, you could use the theorem that says if a line segment intersects two sides of a triangle and is parallel to the third side, the triangle formed is similar to the original big triangle. And that would definitely work as well. I also did this question another way using side angle side. So that's the work I'm going to show next. So side angle side means two pairs of proportional corresponding sides with a congruent angle in between. So I already see that angle E is congruent to itself by the reflexive property because angle E is shared between the small triangle and between the big triangle. So in order to see if the surrounding corresponding sides were proportional, I first found the length of EF, which is a side from the small triangle, and I found the length of the corresponding side from the big triangle, EH, both using the distance formula. I found radical 17 for EF and radical 68 for EH. Simplifying radical 68, I got 2 radical 17. So we can see that they are proportional by a scale factor of 2. If we take radical 17, we multiply it by 2, we get 2 radical 17. So all we have to do now is find the length of EG, another side from the small triangle, and EJ, the corresponding side from the big triangle, and see if those corresponding sides are also proportional by the same scale factor of 2. So once again, using the distance formula, for the length of EG, I found radical 32, which simplifies to 4 radical 2. And I found the length of EJ to be radical 128, which simplifies to 8 radical 2. So we can see once again, if we take 4 radical 2, double that is 8 radical 2. 4 times 2 is 8. So once again, we have that the scale factor is 2, showing that both pairs of corresponding sides are proportional by the same scale factor of 2. So we do have SAS. So I have my reason written up here, so definitely take a second and look. Remember, once again, anytime you're writing a coordinate geometry proof, you do need to have a sentence or multiple sentences in words explaining what your calculation showed and what you actually proved. The third way that you could have approached this problem is by side, side, side. That would have been the same as the way that we did it here with side angle side, except instead of using the congruent angle in between, you would have also found the length of FG and HJ and showed that those sides were also proportional by the same scale factor of 2. The next question that we have over here is a proof question. So I'm just going to hide the proof for a second so we can just really quickly talk about the plan. So here there's really only 2 triangles, but remember our first step if there's multiple triangles in the diagram is to determine which of the 2 triangles which 2 triangles we are focusing on. So SX is right over here. Let me highlight that a bit better because that was awful highlighting. There we go. YW I see is over here. Oh, I gotta make a change to that. That's what was confusing me here. So we have to change YW. Notice how YW is not like a side of any of the triangles. So instead of YW, so also SV, if you take a look, is from this other triangle. So we actually need 2 corrections because if you take a look, WT is not from any of the triangles either. Sorry about that. Definitely made error there in the question. So I'm just going to change this to yx, because that is aside from the yellow triangle. So we're focusing on this yellow triangle over here. And I'm just going to change WT. I want the corresponding side to XY. So I'm just going to change it to VT. And then that should be all good. Let me highlight VT. That's right over here. So that tells us that this pink triangle is the second triangle that we are focusing on. Okay. So now that we know which two triangles we're focusing on by looking at our proof statement, which needed some corrections here, don't worry, on the test we won't need any corrections. We are all ready to think about how we're going to prove this product. So we know that there are 3 steps to proving a product. Number 1, we need to prove triangles are similar. Number 2, prove a proportion. And then finally, we can prove a product. So our first step is to figure out what makes these 2 triangles similar to each other. So from our givens, we know that YSTW is a parallelogram, and we have perpendicular lines. So let's start with the perpendicular lines. So we know that perpendicular lines form right angles. So SX and YW make a right angle here. SV and WT make a right angle over here. So we already have one pair of congruent angles, the right angles. Now let's think about where we can get a second pair of congruent angles for the parallelogram in our 2 triangles. So usually it's helpful to use the fact that opposite sides are parallel, but notice here that we don't really have transversals intersecting YW and ST or YS and WT. So in this situation, I'm actually going to use the fact that opposite angles of a parallelogram are congruent, because opposite angles Y and T are each in the triangles that we need to prove similar. So that gives us our second pair of congruent angles. So whenever you're working on a triangle similarity proof and you have a parallelogram as part of your given information, either see if you can use the fact that the opposite angles are congruent, like we had used here, or see if you can use the fact that opposite sides are parallel to look for angle relationships like alternate interior angles. Now that we know the 2 triangles are similar by AA, we have to think about what proportion we're going to prove in order to prove the product here. So an easy way to do that is start with SX. That's one of the extremes, and I'm going to divide it by the other extreme, VT. And then I'm just going to take one of the means, SV, and divide it by the other mean, YX. And that should give us a valid proportion, but we should double check it by cross multiplication. First, let me just circle. So those were the extremes that we divided. And these were the means that we divided to make our proportion. Remember, the extremes are the outer terms, and the means are the inner terms in the product. We should always double check by cross multiplying. So let me just cross multiply. SX times YX is SX times YX, which is what we're looking for. And SV times VT is SV times VT, which is what we're looking for. So that's a perfectly valid proportion. So I have the proof written up here, so definitely feel free to pause. Everything that we put in our plan is mentioned here in the proof, but I want to draw your attention to the 2 steps that come after proving the triangle similar. Here we have our proportion, and I have to make the changes that we made to the names of the segments. So we had changed YW to YX in order for the question to make sense. And we had changed WT to VT in order for the question to make sense. Let me make that change down here as well. Perfect. So in order to prove the proportion, remember it's the same reason every single time. Corresponding sides of similar triangles are proportional or in proportion. Either one is valid. And finally, to prove the product, that's our last step. Our reason is, in a proportion, the product of the means equals the product of the extremes. Once again, same reason every single time you're proving a product. So these last 2 steps, the reasons are always the same anytime you're proving a product. Same reason for proportion, same reason for products. Make sure that the proportion that you're proving does cross multiply to give you the product that you're looking to prove in the question. The next question is about dividing segments into a given ratio. So I'm going to do it both ways, graphically and algebraically, and feel free to do it whichever way that makes more sense to you. Okay, so let's do it graphically first. So I just went ahead and just graphed my start point x and my end point y. We are told in the question that this is a directed line segment, so that means it does have direction. And it does say from point x, so that's our start point, to point y, so that's our end point. So that's something also to keep in mind. So the first thing I'm going to do graphically is I'm going to see how many spaces we need to move over and up to get from point X to point Y. So sorry, my lines aren't very straight, but I'm just going to count the boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm going to count the boxes up. 1, 2, 3, 4, 5, 6, 7, 8. Let me try that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's why we want to make sure that we graph it accurately, because we want to count the number of boxes correctly when we're doing it graphically. Otherwise, it really could mess up our answer. So I see that we're dividing the segment in a ratio of 1 to 5. So that means that we're dividing the segment into 6 pieces or parts in total, because 1 plus 5 is 6. So what I'm going to do is I'm just going to divide the 12 by 6, and I get 2. And I'm just going to divide the 9 by 6, and I get, hold on 1 second, I get 1.5. I'm going to just leave it as a decimal because it's going to make my life easier with graphing. This is not going to be a super easy one to graph, but that's okay. We'll do it algebraically afterwards as well to double check our answer. So we took our change in x and our change in y, and we divided by the total number of parts that we're dividing the segment into. So up and down, that's our rise. So our rise is going to be 1.5. And left and right, that's our run. So our run's going to be 2. So we're going to be moving up by 1.5 spaces and to the right 2 spaces in order to divide up our line segment. So starting at point X, I'm going to go up 1.5 spaces and over 1, 2 spaces, and I'm going to mark that. Then I'm going to go up 1.5 spaces and to the right 2 spaces, and I'm going to mark that point. I'm going to go up 1.5 spaces and to the right 2 spaces, and I'm going to mark that point. Then I'm going to go up 1.5 spaces and to the right 2 spaces, and I'm going to mark that point. I'm going to keep going because I'm not at point Y yet, the other endpoints. I'm going to go up 1.5 spaces and to the right 2 spaces and mark that point. And then finally, I'm going to go up 1.5 spaces and to the right 2 spaces, and I end up at the other endpoint Y. And if you end up at the other endpoint, that means you did a good job. That means you did everything right graphically. So notice how there are 1, 2, 3, 4, 5, 6 parts of the line segment. So everything we did is good because our goal was to divide up this line segment into 6 parts in total, so we can find that 1 to 5 ratio. So now I see, including the endpoints, there are 1, 2, 3, 4, 5, 6, 7 points here on this line segment. So we have to find which is the point that we're looking for that divides the segment into the 1 to 5 ratio. So I want the 1 part of the ratio, since it's written first, to be closer to the start point, which is x. And I want the 5 part of the ratio to be closer to the end point, which is y. So when I pick the point that is the point we're looking for, I want there to be 1 point towards x and 5 other points towards y. So 1, 2, 3, 4, 5. Looks like it's going to be this point right over here. If it's this point, notice how there is 1 point to the left. That's the 1 part of the ratio. And there are 1, 2, 3, 4, 5 points to the right towards the endpoint y, which is the 5 part of the ratio. So in order to get our final answer, all that we need to do is write down the coordinates of this point. A little bit difficult to see because it's like the half. So that is -4, -0.5. That's what that looks like. It looks like -4, -0.5. And of course, we're going to double check it by doing it algebraically now. If I accidentally wrote down the wrong coordinates, you don't want to do that. It's hard for me to see on the computer screen. Hopefully we got the right coordinates, but we definitely found the correct point. And to me, that looks like -4, -0.5, because it's halfway in between 0 and -1 on the y-axis. But let's double check. So in order to do this algebraically, I broke it down into 3 steps, and it's the same steps for the x-coordinates and for the y-coordinates. And at the end, you'll find the coordinates, the x and y coordinate of the point that you're looking for. So I'm going to start off by finding the change in x, which is x2 minus x1, if that's unfamiliar to anybody. And I'll do the steps for both at the same time. The first step for the y-coordinates is the change in y, so that's y2 minus y1. Remember, we do have a start and an end point. So x2 is going to be 6. X1 is going to be -6. And that gives me 12. And for the y-coordinates, y2 is going to be 7. Y1 is going to be -2. And that gives us 9. Now, we're going to take our end result from step number 1, and we're going to apply step 2 to our end result. And step 2 is to multiply by fraction. So what that means is we're going to turn our ratio into a fraction, but not the way that we usually turn ratios into fractions. We're not going to just write 1/5. We talked about before how 1:5 ratio means 6 parts of the line segment in total, because 1 plus 5 is 6. So when we make our fraction, we want to put 6 as our denominator because there are 6 parts in total in a 1:5 ratio. 1 plus 5 is 6. And on the top, we're going to put the part of the ratio closer to the start point, which is 1. So the fraction that we're going to be multiplying by is 1/6 in order to correctly divide up the line segment into the 6 parts that we need for this ratio. So I'm going to take 12, our result before, and multiply it by 1/6, the fraction that we just came up with, and I get 2. And I'm also going to take for the y-coordinates the result that we got before, which is 9. And I'm going to multiply it by our fraction, 1/6. I get 9/6, which is 1.5. Then finally, all we need to do is add the starting x-coordinate to our result and add the starting y-coordinate to our previous result. What that means, for starting x-coordinate, it's the x-coordinate from our start point. And for starting y-coordinate, what that means is the y-coordinate from our start point. So I'm going to take our result 2, and I'm going to just add the starting x-coordinate, which is -6. And that gives me -4. I'm also going to take our result here for the y-coordinates, 1.5, and I'm going to add the starting y-coordinate, which is -2. And feel free to use a calculator if you need to, but you should get -0.5. So now we have the x-coordinate of the point that we're looking for and the y-coordinate of the point that we're looking for. And notice how we got the exact same answer for our point graphically as we did algebraically. So you can do whichever way makes more sense to you. You don't have to do both. Either way that makes sense to you is the correct way to do it for you. There's also a video specifically on this topic on Google Classroom under helpful math resources. It's about a 10-minute video on it going through both ways. The video I recorded last semester. So if you want to see this done again with a different problem, I would recommend to definitely check that out. Okay, so this is a word problem here, and a lot of it's filled into the diagram for us, which is really, really nice. Let me just read through it once to refresh my memory on what it's asking for. So in the diagram below, the line of sight from the park ranger station P to the lifeguard's chair L on the beach of a lake is perpendicular to the path joining the campground and the first aid station. So that explains where the right angle here came from, because this is perpendicular to that. The campground is 0.25 miles from the lifeguard chair. So that's why the 0.25 is here. The straight paths from both the campground and the first aid station are perpendicular. So that explains why we have the right angle here as well. The path here is perpendicular to the path here. So that explains why we have a right angle. So I didn't really read the rest of the question yet, and I'm going to in a second, but already I'm seeing a couple of things to look out for. I'm seeing right triangles, something to definitely keep in mind. And I'm also seeing a big right triangle with an altitude drawn to the hypotenuse. So we might keep in mind right triangle altitude theorem also. That's what this diagram setup looks like. It looks like a perfect setup for the right triangle altitude theorem type question. If the path from the park ranger station to the campground is 0.55 miles, okay, park ranger station to campground, that's why this is 0.55, determine and state to the nearest hundredth of a mile. Let me just circle that for a second. Hundredth of a mile is 2 decimal places. So I just want to indicate that. Tenth is 1 place. Hundredth is 2 places. Thousandth is 3 places. Any more than that, they would probably just say 4 decimal places or 5 decimal places. So the big ones now are tenth, hundredth, and thousandth. That's 1, 2, and 3 decimal places. So we're determining and stating the distance between the park ranger station, so that's P, and the lifeguard chair, that's L. So we're finding the altitude. Okay, so let's tackle that part of the question before we answer the second part, which I didn't even read yet, to be honest with you. So, um, since it is the perfect setup for right triangle altitude theorem, and we are finding the altitude drawn to the hypotenuse of the big right triangle, I'm going to ask myself, can I use the altitude rule? Remember that for the altitude rule, the altitude is the mean proportional between each part of the hypotenuse. But here, since we're looking for the altitude, that's a variable because we don't know what it is. We do know this part of the hypotenuse, but we don't know the other part of the hypotenuse. So we would have to make that a variable as well, which we can do. And you're more than welcome to try it out. But I just think it would get really, really complicated. And there's a much easier method to do this. But it is good that we think about this is the type of situation where if we did have the information, the altitude rule would be absolutely perfect for finding the altitude if we did have this part of the hypotenuse as well. But luckily for us, the altitude is a side of the smaller right triangle that I just outlined in red. And in the smaller right triangle, we have 2 sides. We have LC 0.25 and we have PC 0.55. So we just need to find the third side of this right triangle. So we can definitely use Pythagorean theorem. Remember, Pythagorean theorem is a squared plus b squared equals to c squared. You need to be really, really careful with the Pythagorean theorem because c always represents the hypotenuse. So I'm going to put that here, hypotenuse. And the hypotenuse is always opposite from the right angle. So here would be the hypotenuse of this triangle. So we need to make sure that in for c, we are plugging in 0.55. So we have 0.55 squared. And then for one of the legs, we have 0.25 squared. And then the other leg is PL, which I don't know, so I'm going to make that x squared. Let's use our calculator to kind of simplify what we can. So type in 0.25 squared. You're going to want to put parentheses around the 0.25 before you square it in order to get an accurate value. So I got 0.0625 on my calculator when I did that, plus x squared is equal to, I'm going to type in 0.55 squared. Remember once again to put parentheses around the 0.55 before you square it. And I got 0.3025. So I'm going to subtract 0.0625 from both sides in order to solve for x. So I'm subtracting 0.0625. And I got x squared is equal to 0.24. So I have x is equal to the square root of 0.24. I'm not going to do anything else with that. It says, almost forgot. It said determine and state to the nearest hundredth of a mile. So it wants us to round to 2 decimal places. So I'm actually going to type radical 0.25 into my calculator, and I'm going to see what I get for that. So I typed it into the calculator on my computer just so you guys can see it. And when I did the square root of radical 0.24, I got 0.48989794855, that long number that goes on forever because it's irrational because it's a non-perfect square radical. So we need to round to 2 decimal places. So 4, 8, I'm going to look to the number next to it, which is 9. So that tells me to round the 8 up 1 because the 9 is greater than 5. So this is going to be approximately 0.49. So let me go back to the question we were doing. So x is approximately 0.49 of a mile. So we determined and stated the distance between the park ranger station and the lifeguard chair. So we're done with the first part. Let's take a look at the second part. Gerald believes the distance from the first aid station to the campground, so from F to C, is at least 1.5 miles. So Gerald believes that if he goes from point F to point C, that it's going to be either 1.5 miles or more because it's going to be at least 1.5 miles. So he thinks that it's probably more than that. It could be 1.5, but like it's definitely not going to be less than that. So let's see if Gerald is correct in his belief. So in order to just get a better picture of what is going on here, let me just fix up my diagram a bit. So now that we found what PL was in the first part, I'm just going to replace that X with what we found, 0.49 of a mile. And the reason for that is because now, remember at the beginning, we were talking about using the altitude rule because we were finding the altitude, but we didn't really have enough information because we didn't know the other part of the hypotenuse or the altitude, so we would have had 2 unknowns. Well, now since we want to find FC, which is the whole hypotenuse over here of the big right triangle, if we could find FL, and I'll represent it as Y just because we used X last time to find the altitude, so I don't want anybody getting confused. So if we find FL, this part of the hypotenuse, we already know this part of the hypotenuse, so we can add them together and get the whole thing. So now we can actually use the altitude rule to find the missing part of the hypotenuse because we found what the altitude was. So I'm going to do that over here. So according to the altitude rule, the altitude, which is 49, is the mean proportional between each part of the hypotenuse. So one part of the hypotenuse is FL. We don't know what it is, so I'm going to label that as Y. The other part of the hypotenuse is LC, and that's 0.25. So I'm just going to cross multiply and solve for Y. So I have 0.25Y is equal to, I'm going to get my calculator out, and I'm going to do 0.49. Oops, I typed it in wrong. 0.49 times 0.49. And I get 0.2401. And then I'm just going to divide both sides by 0.25 to get Y by itself. So I'm going to divide by 0.25. And I got 0.9604. So remember, Y just represents from F to L. It doesn't represent the whole thing from F to C. So I'm going to just get rid of this Y here for a second. And I'm going to replace it with what we just found Y is, 0.9604. So now to find out what the whole length of FC is to see if Gerald is right, I'm going to just add the 2 parts together, 0.9604, and I'm going to add 0.25 to it. And on my calculator, when I add them together, I'll just put it over here, 0.9604 plus 0.25. I get 1.2104. So Gerald believed this distance was going to be at least 1.5 miles. He said it was going to be 1.5 at least, maybe more, but definitely not less. So I see that Gerald is not right because the distance is actually about 1.2104 miles. So Gerald was close. It's close to 1.5, but he's not right. It's not 1.5 or greater. It's not at least 1.5. So I'm going to write Gerald is not correct. So I'll just write no, but you should write Gerald is not correct. And it says justify your answer, not explain. So justify just means show work. You don't have to write anything in words unless you want to. as long as your work supports how you got that Gerald is not correct. So all our work here supports that Gerald is not correct. This is not at least 1.5 miles. It's less than 1.5 miles.